The best way to understand a complicated notion like compactness is to view it from more than one perspective. We have already characterized compact sets as precisely those that are closed as well as bounded. Now I'm going to give a slightly more abstract way of dealing with compact sets, that is via open covers. So we begin with a definition. This is the definition of an open cover and finite subcover. Let A subset of R be any set. The collection of open sets, script O, which is some OI, I coming from some indexing set, is said to be an open cover of A if A is a subset of union of all these open sets OI. Okay, so this is a fairly straightforward notion. You say a collection of open sets is an open cover if the union covers the set. We say a finite subcollection or rather we say O has a finite subcover if we can find I1 I2 ik in the indexing set I such that A is a subset of union or rather OI1 union OI2 union union OIK. So if you have a finite subcollection that covers the set A, then you say that O has a finite subcover. Okay, so these two definitions are fairly straightforward, but they actually have a lot to do with compact sets, which is not at all clear because the definition of compact sets had nothing to do with open covers or anything. It just said that a set is compact if every sequence has a convergent subsequence. So first let's see an example, or let's see several examples. Any finite set that is covered, or better way to phrase it is any open cover of a finite set admits a finite subcover. Example 2, consider the set open AB. Okay, we claim that the cover ON defined to be A plus 1 by N comma B, where I choose N such that 1 by N is strictly less than B minus A. Okay, has no finite subcover. Okay, we are considering the open set AB. We are considering a very special cover, and the claim is that this cannot have a finite subcover. Why is that the case? Well, let's see. suppose it has a finite subcover. It has a finite subcover. Okay, let On be, or OM be such that M is the largest index in this subcover. Well, this is a finite subcover. It consists of elements of the form A plus 1 by n comma B. There must be a largest such M. Okay, then clearly the union of this subcover is OM, right? Because as n becomes large, A plus 1 by n contains A plus 1 by m if n is greater than m, right? So this m is the largest index, so all other indices are less than m. Therefore, A plus 1 by m comma b will have to contain all such subindices, all such sets of the form A plus 1 by n comma b, right? So this means we are in the peculiar situation that AB is a subset of A plus 1 by m comma b, which is nonsense. Right? So open interval AB has a cover that has no finite subcover. Okay. Now, third example, let S subset of R be an unbounded set. Then consider the cover minus n comma n such that n in natural numbers, or I put z, let me just make it n. Again, easy to see that this cover has no finite subcover. Okay. A fourth example, consider the set 1 by n union set with 0. Okay. Let O be any open cover. Let me call this set A, be any open cover of A. Okay. Then notice that for some O1 in O, 0 belongs to O1. Right? Because this is an open cover of A, some element in this cover has to contain the element 0. Right? But 1 by n converges to 0, so all but finitely many terms must be in O1. Now it is easy to extract a finite subcover. I just choose various elements from this cover O that contain the first few elements of the sequence. Beyond these first few terms, all the terms of the sequence have to belong to this set O1, just because 1 by n converges to 0. Okay, now we have seen several examples. These examples should sort of suggest to you that this is an equivalent characterization of compactness. The characterization is as follows. A set is compact if and only if every open cover of the set has a finite subcover. Now this notion of open covers seems a fair bit more complicated than that of just compactness defined via sequences. I am going to show this theorem that a set is compact if and only if every open cover has a finite subcover. Here is a proof tip. When trying to connect two seemingly different concepts, try to come up with some intermediate chain that connects the two. Now here I want to connect sequential compactness, that is, a set is compact if any sequence has a convergent subsequence that converges to an element of the set, with this notion of open covers and finite subcovers. Okay, so what I will do is I will state a intermediate concept that ties both. Lebesgue number of an open cover. Okay, suppose O is an open cover of A. A Lebesgue number, note this choice of word, it's a Lebesgue number delta greater than 0 for this cover with respect to A is a number that satisfies B x delta is contained in some element of O. Let's say, I'll just give it a name for concreteness, a subset of OX, which is an element of O. So for all x in A, B of x delta is contained in OX, which is an element of O. Note the order of quantifiers. What this is saying is you pick an element x of A and consider the ball of radius delta centered at x. There will be a corresponding OX in this cover O such that Bx delta is fully contained in OX. Okay. Note, you will understand why I said a Lebesgue number. If delta works, certainly delta by 2 will also work as a Lebesgue number. So will delta by 3, so will delta by 10,000. Right? So, a Lebesgue number for an open cover with respect to a set A is some sort of uniform estimate on how the collection O covers this set A. Okay? Now here is the key theorem, or rather lemma. This is called the Lebesgue covering lemma. The Lebesgue covering lemma. Suppose A is a compact subset of R and O an open cover. O an open cover. Then O admits a Lebesgue number with respect to A. If you have a compact set and some open cover, then that open cover has a Lebesgue number with respect to this compact set. Proof. So this Lebesgue covering lemma is going to be the connection between open covers and compactness. So let's do this proof in great detail. Okay. Suppose there is no Lebesgue number for O with respect to A. This means each 1 by n fails to be a Lebesgue number, right? There is no Lebesgue number, therefore 1 by n cannot be a Lebesgue number. Okay? Now, how do we exploit this? Because each 1 by n fails, for each n in the natural numbers, we can find xn in the set A such that for all O in this script O, B xn 1 by n is not a subset of O, right? What is the condition that a particular number is a Lebesgue number? It's a number such that for each element x in the set A, B of x delta is subset of OX for some element OX coming from the cover O. No 1 by n can be a Lebesgue number. That's our assumption. That means no matter what n you choose, 1 by n fails to be a Lebesgue number. So somehow the definition of Lebesgue number is not satisfied for 1 by n. That can only happen if you can find a point xn such that B xn 1 by n is not an element of O, and this must be true for all the sets O coming from the collection script O. Right. Now you can guess what's going to happen. Observe that some subsequence x and k must converge to x in A. Why? By compactness. Compactness ensures that there will be a subsequence that converges to an element in A. Okay. Now what do I do with this? Well, I will state it this way. Let OX in O be an open set such that X is in OX. Why is there such an open set in the collection? Oh, simply because this is an open cover of A. So every element of A has to be present in at least one element of the cover script O. Okay. So I'm just picking an open set OX such that X is in OX. Okay. Because OX is open, we can find some epsilon greater than 0 such that B x epsilon is contained in OX. Now we are getting somewhere. We have found a ball bx epsilon which is fully contained in OX. Okay. Now choose nk so large that 1 by nk is less than epsilon by 2. Okay. Okay. But x and k converges to x, right? So let me not use the word nk here. Let me just use capital N so that there is less confusion because of notation repetition. But x and k converges to n, x and k converges to x, so we can find some, let's say m greater than n, not m, some x and m, some nm greater than n, such that mod x and m minus x is less than epsilon by 2, right? Because x and k converges to x, we can find nm greater than n such that x and m minus x is less than epsilon by 2. Okay. Now let me change the notation slightly. I don't want to give the indication that x and m is a different subsequence. All I mean is m naught. Okay. Fine. Now mod x, no, just a second. Notice that because b x epsilon is contained in OX, we immediately get x and m naught is an element of bx epsilon, and this is a subset of x. Okay. And not only that, because mod x and m naught minus x is less than epsilon by 2, we get the set y such that mod y minus xm naught less than epsilon by 2, this set is going to be a subset of bx epsilon. This is going to be a subset of bx epsilon. Why is that the case? Well, mod y minus x and m naught is less than or equal to mod y minus mod y minus x is less than or equal to mod y minus x and m naught plus mod x and m naught minus x, right? But this is less than epsilon by 2, and this quantity is also less than epsilon by 2 because nm naught is strictly greater than n, and we have this condition. Together this claim, this shows star. Well, what's the net consequence of all this? We have got b x nm naught comma epsilon by 2 is fully contained in this element OX. But wait a second. 1 by nm naught is less than epsilon by 2, right? Why is that? Because 1 by n itself is less than epsilon by 2. Therefore, 1 by nm naught is less than epsilon by 2. Wait a second. That means b x nm naught comma 1 by nm naught is contained in OX. But this contradicts the definition, or rather the choice of nm naught. We had intentionally chosen this point xnm naught as a point such that no element in this open cover can contain bxnm naught comma 1 by nm naught. But we have shown that bxnm naught comma 1 by nm naught is contained in OX. This proves the theorem. This proves the lemma actually. Okay. So this is a somewhat involved proof, but this acts as the intermediary that allows us to move from compactness defined via sequences and subsequences converging to this more abstract notion of open covers. In the next module, we will show that open covers having finite subcovers is just a different formulation of compactness. This is a course on real analysis, and you have just watched a module on open covers and compactness.